All right, ready for combinations? Yay. So a permutation is an ordered arrangement of objects. A combination is unordered. So C n comma r equals the number of unordered arrangements of R objects from a set of n. So you play poker, you pick 5 cards out of a deck of 52. And once you've got your hand of 5 cards, you can move them around in whatever order you want in your hand. If you have a 2, 3, 5, 7, 8, it's exactly the same hand as an 8, 2, 3, 5, 7. The order doesn't matter. So the number of unique hands that you can get when you get 5 cards out of a deck of 52 is just the number of 5 combinations of 52 objects. And this is equal to the number of ordered arrangements divided by the number of possible orders. So how many ways can we arrange 5 objects? That's just 5 factorial. So C52.5 is just P52.5 divided by 5 factorial. And in general, Cn comma r is just Pn comma r divided by r factorial. So you take all the ordered arrangements and then you divide out the number of possible orders because they're all considered to be the same. So Pnr is n factorial over n minus r factorial. And we divide that by r factorial. There's your formula for the number of combinations. I thought I fixed that. It looks horrible. I'll make it worse. Yeah. All right, so CNR is n factorial over n minus r factorial times r factorial. So the number of 5 cards from 52 is 52 factorial over 47 factorial times 5 factorial. Which is not as horrible a number as it looks because this 52 and this 47 factorial, most of those terms cancel. This will actually end up being 52 times 51 times 50 times 49 times 48. And the other terms, 47 to 1, will cancel with this, and then you just divide by 5 times 4 times 3 times 2. So pick 5 people out of a group of 12. And the order in which I pick these 5 people doesn't matter. I'm just choosing 5 people. They're each going to win $100. So the number of ways that I can pick 5 people out of 12 is just the number of 5 combinations of 12 objects, which is 12 factorial over 12 minus 5 factorial times 5 factorial. Suppose I have a group of 10 people and I want to pick 10 people from that group. How many ways can I do that? it's really just one way I'm going to pick the 10 people, right? But this is C10 comma 10, which is 10 factorial over 10 minus 10 factorial times 10 factorial, and that is in fact 1. Okay, here's a 250 question. How many n-bit strings contain exactly R ones? So suppose R is 3 and N is 8. How many 8-bit strings contain exactly 3 ones? And we can think of this as saying, if it's an n-bit string, we have n bit positions, positions 1, 2, 3, 4 up through n, and we're trying to pick R of those positions to contain a 1. So we can think of this as saying, how many ways can we select R positions to contain a 1 from n possibilities? And that's just the number of R combinations of n objects. And the order that we pick these R positions doesn't matter. If I say I'm going to put a 1 in bit positions 3, 4, and 7, that's the same number as if I say I'm going to put a 1 in bit positions 7, 4, and 3. Right? So the order in which I pick these 3 bit positions makes no difference. So it's a combination question, not a permutation question. And this is n factorial over n minus R factorial times R factorial. Well, if we think about this question, we can start seeing some interesting things here. So let's just keep with this question, n-bit strings containing R1s. Let's fix n at 8. So we're thinking about 8-bit strings. How many 8-bit strings contain 3 1s? That's Cn comma 3. So that's the number of things with 3 1s. How many 8-bit strings contain 2 1s? C of n2. C of n1 is the number of strings containing a single 1. C of n0 is the number of 8-bit strings containing 0 1s. And so on. Well, if I add all of these together, what should I get? Don't do the math. What should I get if I add these together? This is the number of strings containing 3 1s. This is a number containing 2. This is a number containing 1, 0, 4, 5, 6, or 7 1s. Have I covered every possible 8-bit number? Because every 8-bit number has either 0, 1, 2, 3, 4, 5, 6, or 7 1s in it. So if I add up the number of these, I should get the number of 8-bit numbers, which is just 2 to the 8th, 256. But if I write these out, right, what I'm going to get is something like 8 factorial times over 0 factorial times 8 factorial plus 8 factorial over 1 factorial, 7 factorial. That's going to come out to be a power of 2. So we've got some weird connection between factorials and powers of 2, which it's not obvious there should be such a connection, because powers of 2 is like the simplest thing. You just multiply by 2 a bunch of times. Factorials are kind of the most complex thing, because you multiply by successive numbers a bunch of times, but they're related to each other. And we'll come back to that in a bit. Well, Cn3 is the number of strings containing 3 ones. What would be a formula for the number of strings containing 3 zeros if I had made that my initial question? How many 8-bit strings contain 3 zeros? And we might have said, on the flip side, how many 8-bit strings contain exactly R zeros? How can we select R positions to contain a 0 from n possibilities? It's going to be CNR. So Cn3 is the number of strings containing 3 zeros. Also, it's the number of strings containing 3 ones. But if a string contains 3 zeros, how many ones does it contain? It's an 8-bit string, so it's got 5. So we've just shown that C of n3 equals C of n5.
But isn't one of them have to be 0 and one of them have to be 1?
Yeah, but this is the number of strings containing 3 ones. But it's also the number of strings containing 3 zeros, which means it's number of strings containing 5 ones. So there's some symmetry between these. So in general, C of nr is going to be the same thing as C of n minus r. And if you plug those into your formula, you're going to see your denominator down here is exactly the same. That's going to become an n minus r, and that's going to become an r. So lots of symmetries. Well, let's draw a picture, because that's what symmetries inspire us to do. So shout when you've seen this. Seen it? Okay. It's Pascal's triangle.
Wow.
And it goes on. And this is the same thing as C00, C10, C11, C20, C21, C22, and so on. But the way I'm drawing Pascal's triangle is simple. I start and end with a 1 on each row, and each number is the sum of the 2 numbers right above it. So if I wanted to make another row of this, I would start with a 1. 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and then there's a 1 at the end. And you can immediately see the symmetry, right? That C of nr and C of n minus r are the same value. So let me draw this out a little further. can do this all day. But I'll stop there. And what I've written down are, in fact, these big factorial formulas, n factorial over n minus r factorial times r factorial. Guaranteed it's going to give me these values. Right, but I can get it by just adding these numbers above each row. Well, let's play with this for a few minutes. So what do I get if I add the elements in this first row? I just get a 1. What if I add the elements in the second row?
2.
Third row?
4.
Next row?
8.
You see the pattern? So assuming I label my rows starting from 0, the sum of the elements across any row is just 2 to that row number. And that's what we were sort of dancing around with, this number of zeros, number of ones in an n-bit number. And I mentioned if you add up these combinations, you end up with a power of 2. Well, that's what we're doing here. Each of these is a combination, and if you add them up across a row, you get the next power of 2, which is kind of cool. So what if we add the square of each element? So 1 squared is equal to 1. 1 squared plus 1 squared is still 2. 1 squared plus 2 squared plus 1 squared is 6. 1 squared plus 3 squared plus 3 squared plus 1 squared is 20. Let's do one more. I won't tell you this one. Someone tell me. 70. So if we add the squares of the numbers across each row, we get these peculiar numbers. But there's a 1, there's a 2, there's a 6, there's a 20, there's a 70. So if you add up the square of the elements on row R, you get the middle element on row 2 times R, which is kind of cool. Okay, let's look at each row and let's ignore the ones. So we won't look at the first row or the second row because there's only ones there. But starting down here, row 2, we'll ignore the ones. So we're looking at row 2 and the only element on here is 2, and 2 is a multiple of 2, correct? Okay, so I'm going to mark that with a check mark. Let's go down to row 3. The elements on this row are 3 and 3. Are both of those multiples of 3? So I'm going to mark that with a check mark. Let's go to row 4. The elements in the middle are 4, 6, and 4. Are all of those multiples of 4? No, so we're going to put an X next to that. How about 5, 10, 10, 5? All multiples of 5? 6, 15, 20, 15, 6. All multiples of 6? Nope. 7, 21, 35, 35, 21, 7. Multiples of 7? Okay, 8, 28, 56, 70? No. I have to go one more to make it interesting. So we'll go with 1, 9, 36, 84, 126, 126, 84, 36, 9, 1. All multiples of 9?
Yes. No.
Yes or no? It's one of those.
84 is not.
Yeah, 84.
84 is not divisible by 9. So we got an X here, so it's not just the odd numbers, but it is the numbers 2, 3, 5, 7. So what's the hypothesis here? Prime numbers, and that's what it turns out to be. If you're in a prime numbered row, every number except for the ones will be a multiple of that row number. So there's a really weird way to test primality. All right, one more weird property. 11 to the 0 is equal to what? 11 to the first is equal to 11 squared.
122.1.
11 cubed.
1, 2, 3, 2, 1.
I don't think so.
1, 3, 3, 1.
Well, you got to do the work.
1,330.
1331, good. Got your calculator out. Go ahead and do 11 to the fourth. There we go.
14,641.
Yay. All right, so what's happening here, right? 1, 11, 121, 1331, 14,641.
That's really cool.
It kind of breaks when you get to 11 to the fifth.
Yeah, I was gonna say.
So what did you get for 11 to the fifth?
161,051.
And it kind of breaks because 10's not a digit, right? But if we sort of carried stuff over, this would become an 11, which would become a 1, and this would become a 6. So you get 161,051. So you could actually work in a different base, and 11's magic because we're working in base 10. But if we were working in base 20, we would find each of these rows was a successive power of 21. And that comes back from this idea that each entry here is the sum of the two entries above it. And if you multiply a decimal number by 11, what are you doing? You're taking your number, and then you're writing it down, shift it over one spot, and then you're just adding. That's pencil and paper multiplication, but that's basically what's happening in here. So about 4 years ago, we were talking about this in 215, and the class got into a discussion about it, and I mentioned the possibility of working base infinity, in which case this would work forever, because you'd never find a number that was bigger than your base. And one of my students in the front row, her brain kind of went into a different mode, and she went off for a few days, and she invented this base infinity number system. And she may still have a poster up on the wall. This became her SLP, and she actually presented this at a math conference a couple of years later. So this stuff can get you into weird territories. So that's a little bit about Pascal's triangle, and it's tightly bound in with combinations, so it comes up in probability a lot, which I think was what Pascal was originally working on. But it also has all these beautiful symmetries inside it. So a bit of notation when we talk about the number of R combinations of n objects. There's a different way you'll see this written in the book and elsewhere. This is sometimes written just like this. So parentheses with n on top and r on bottom. It's not n divided by r. If you draw a line here, you're just dividing something. But parentheses with two numbers, one on top of the other, means the number of r combinations of n objects. It's just a different way of writing it. So Pascal's triangle is actually 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, and so on.
So what about the P?
Permutations?
Yeah, permutations.
Mm-hmm.
Is it written the same way?
No. This is just for combinations. I don't know why. Permutations, we always just do P, parentheses, n comma R. But I think combinations might be used more often. Well, we got 10 minutes.
The general theory proof about everything being written in terms of ones and zeros. Does that let you do weird stuff in hashing? Is that used, or is that just a neat thing?
Maybe. Yeah, it probably comes in. It definitely comes in,
Okay.
right?
I mean, like.
So I mean, that tells you if you
clearly-
have n entries in your array and you try to hash n plus 1 words, you're going to have a collision.
But I was curious about the whole A minus B.
I don't know if there's a way to use that. I'll bet there is.
Yeah, it
Yeah.
seemed like I thought about it and I was like, I'm sure there's some way you can use it, but that's so weird I couldn't think of anything off the top of my head.
Think about it more. I bet you come up with something. And then you can publish a paper on it. All right, so normally I would talk about binomial coefficients, but you know, every time I've talked about this, I'm convinced it never really makes sense. And we've only got 10 minutes, and I definitely want to go on to something else next week, or Friday rather. So let me just start in with something else, but take a look in the book, I think it's in there, on binomial coefficients, and there might be a homework question about it. If there is, I won't grade it, but I'd like you to think about it and ask questions about it anyway. But let me go on to something else, since we're talking about cool combinations of numbers. Shout when you know what this is. Okay. So what is this? This is a Fibonacci series.
Takes the last two numbers and add.
Yeah, so each number you take the two numbers before and you add them together. So the next number in the sequence would be 34 plus 55, which is 89, and so on. And this is a famous series. It pops up in all kinds of places, not just in mathematics, but also in nature.
Golden ratio.
Golden ratio, yeah. Pine cones, sunflowers, all the good stuff in life. So, and there's some interesting properties here. For example, if you take any number and you square it, and you take the numbers on either side and you multiply them, those two things are always within one of each other. So 8 squared is 64, 5 times 13 is 65, it's one more. 13 squared is 169, 8 times 21 is 168. It's one less. And it alternates. So there's lots of properties. And if we have Fn, meaning the nth Fibonacci number, we can write Fn as Fn minus 1 plus Fn minus 2. This is for n bigger than or equal to 2. And we can just say F1 equals F0 equals just the number 1. So that completely defines what the Fibonacci series is. But it's not always a convenient way to calculate this. If we want to know what F5 is, this will tell us what's F5. Well, it's just F4 plus F3. Any other questions? Yeah, what's F4? Well, F4 is F3 plus F2. Okay, well, what's F2? Well, F2 is just F1 plus F0. And we know F1 and F0 are 1, so this is 2, so we know F2 is equal to 2. F3 is F2 plus F1. Well, I can cheat. I know F2 is 1 and F1 is 1, so F3 is equal to 3. So that tells me F4 is equal to 3 plus 2 is 5, and F3 I found was 3. So now I know F5 is equal to 8. And sure enough, 0, 1, 2, 3, 4, F5. So this is a nice succinct way of describing each term of the series, but it's not always the most convenient way to actually calculate the nth term. But if you were to write code for this, it's really, really simple code. It's 2 lines of code. So we can let's see if I got some code. I don't have code.
Does the difference thing work because n minus 1 times n plus 1 is equivalent to n squared plus 1 squared?
Yeah, basically. So let's Let's write a Fibonacci function, and let's find the 10th Fibonacci number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That should be 89. So let's write a Fibonacci function in 2 minutes. So there's the function prototype. Okay, so what's our definition of the nth Fibonacci number? Well, if n is 1 or 0, the nth Fibonacci number is just 1. So if n is less than or equal to 1, let's return 1. Let's spell it correctly. So if n is 1 or n is 0, we're just going to return 1. Otherwise, let's take fib of n minus 1, let's take fib of n minus 2, let's add them together, and let's return that. There's our whole Fibonacci function. Recursion. See how many syntax errors I made.
I've never seen a function called in the Princeton statement like that. It's kind of blowing my mind.
Yeah, it's a little
right now.
freaky. So let's run fib. Fib 10 is 89. Yay, happiness. So let's print the 40th Fibonacci number. Oh, that actually worked. Let's print the 60th Fibonacci number. There we go. This will either run forever or it will crash my computer. Whichever comes first. No.
Actually, it might take like 5 minutes because I've tried that. With the 50, it takes around 4.5 minutes. So
Yeah,
60
and 60 I don't think will finish
Yeah.
because the times go up horrifyingly. So what's going on here?
Fib 100 one time. Not cool.
So let's just print out what we're calling fib for. So I'll just say print calculating fib, parentheses, %d, and I'll just print out what I called fib with, just to see what it's doing. And you can see it's just going crazy. It's just calculating fib. And mostly it's calculating these really small values. But every now and then there's a bigger value. So there's a 6, and there's a 10, and there's an 11, and there's a 12, right? And it's just, right? So it's really not going to finish, but it will probably run out of stack space and it will crash my machine at some point. But, you know, the function itself is simplicity. It's 2 lines. We could actually write it in 1 line if we wanted. So this is a recurrence relation, this fact that we can express the nth term in terms of prior terms. And so we're going to play a little with recurrence relations, and we'll see where this Fibonacci series comes from. We'll be talking about bunnies on Friday. And I'll fix my focus issue now that I got color working.